Alright, today we're going to be learning how to graph rational functions that have a polynomial both in the numerator and the denominator. On day 2, we learned how to graph a reciprocal function, which looked like this, if you guys recall. Alright, with your a, h, and k. This is a more simple sort of rational function that we specifically call a reciprocal because of the way that it's set up. This one only has a simple binomial in the denominator, and that's the only polynomial that you really see within the rational function. When we're looking at our rational functions today and for the rest of our unit, they're going to look a lot more complicated. Notice that this only has one x in the denominator, and then all of these other things are just numbers, so it looks pretty simple based on what we're about to see, because you only have one x and everything else is a number. The ones we're going to be talking about in this lesson in order to graph and in the following lessons when we're doing other operations are going to look more like this, where you have an x in the numerator and the denominator. You could also have an x squared and an x, like a trinomial and a binomial. So the ones we're going to be working with now are going to have x's, or polynomials in general, in the numerator and the denominator. So they're going to look a lot more complicated, and not just look complicated, they are more complicated. You can see over here in this box that goes all along the side, all of these things are what we're going to be trying to find for each of these little relatively innocent looking functions here. We're going to have to find horizontal asymptotes, vertical asymptotes, a hole if that exists, x-intercepts, y-intercepts, domain, and range. We have to find all of these things, and they all have different rules that direct you on how to find them. So there's a lot of details to this lesson. Each rule in itself is not complicated. The complicated part is trying to remember all of them at once. So I have this little table here that you guys are going to be using as we're practicing. I also have a separate organizer, like a piece of paper in your notes. I think it's after the homework for this lesson, that also describes all of this in a little bit more detail. So you can use this little table here or that organizer. Just read through it a bunch of times and practice, practice, practice. The more you practice it, the more the process kind of sinks in and the easier it is. But as we're working with it at first, it's going to seem like a lot of stuff to remember, which it is, but you just need to keep practicing. So before we jump into the example, because that's all we really need to do is just practice, 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 I want to remind you guys of some vocabulary. We talked about continuous versus discontinuous on day 2. Remember our reciprocal graphs that we were graphing, or the simpler graphs that we learned last time, looked like this, our hyperbola. They were broken into 2 different parts. That's why we call it a discontinuous. If a curve or a line is broken or has a gap or hole, we call that discontinuous. A continuous graph is when you can draw something in full without any stops or breaks or anything like that. All right, so remember that's the difference between continuous and discontinuous. The things that create discontinuous graphs, so the thing that creates a break, gap, or hole, those are called discontinuities. So discontinuities create discontinuous graphs. The 2 that we're going to be focusing on primarily in this lesson are vertical asymptotes and a hole. A horizontal asymptote is not considered a discontinuity. Because horizontal asymptotes are special because those are the ones that sometimes you can cross, although it's rare. So that's why we don't consider it to be a discontinuity, because there is that rare opportunity where you're actually allowed to pass through a horizontal asymptote, but there is no situation in which you would ever cross a vertical asymptote or pass through a hole. So these are our concrete discontinuities. A vertical asymptote is referred to as a non-removable discontinuity, but a hole is referred to as a removable discontinuity. My understanding of why this one is called a removable discontinuity is because in order to have a hole, you need to have removed or cancel out a factor from your original function. So you're going to see that in a little bit. The way that you know you have a hole is if you were able to cancel something away from your function. So that's my understanding of why it's called a removable discontinuity. It's because you were removing something from the original function to create that hole. All right, so you guys do need to remember the difference between non-removable and removable, because I'm going to be asking questions on, hey, what kind of discontinuity does this function have? And if it's a vertical asymptote, would you consider that non-removable or removable? So you guys have to remember which one is removable, which one's not removable. Okay, So now, what we're going to do is we're just going to do a bunch of examples. We're going to find the same things for each example. We're going to find horizontal asymptotes. We're going to check to see if there's any discontinuities, which means vertical asymptote or a hole, or both. Sometimes you can have both. X-intercept, Y-intercept, domain, and range. So we're going to find all of those things for each of these examples, and then when we get to the next page, I'm also going to add on the idea of how do we graph them, how do we visualize them, which is just doing all the exact same stuff plus a graph. Okay, so we're going to see lots of examples where we get to practice and let this information sink in. All right, so before I get to the example, I'm just going to go read through this and try to explain the rules before we apply them. So there's actually two phases that you guys are going to be working in to find the information for these functions. There's the before phase, which is before factoring or simplifying, and then there's the after phase, which is after you factor and simplify. The only thing that you can find before you factor, so in phase 1, is your horizontal asymptote. So that's the first thing you want to do before you touch your function, before you do anything to it. Like, you put your pencil down, don't even try to cancel or factor anything. Don't do anything to your function, just look at it. That's how we find our horizontal asymptote. There are 3 options for the horizontal asymptote. It could either be 0, it could be the fraction of the leading coefficients for your polynomials, or you could just not have a horizontal asymptote at all. Okay, and this is how we figure out which one of those 3 situations we have. We're going to be comparing the degrees of the numerator and denominator. Remember, degree is the highest exponent for your polynomial. So you're going to find the degree of the numerator and the degree of the denominator. If the numerator's degree is smaller than the denominator, so you're smaller in the numerator, that means that your horizontal asymptote is going to be a 0. If the degrees are the same, so that means you have x squared and x squared, or x and x, or x cubed and x cubed, you have the same degree for both the top and the bottom. That means you're going to take the leading coefficient. Remember, the leading coefficient is the number in front of the variable. You're going to write down the leading coefficient in the numerator and divide that by the leading coefficient in the denominator. And whatever that number is, that's your horizontal asymptote. The other situation that you could have is your numerator's degree is bigger than the denominator. If that happens, we call that top-heavy. If you want to jot that down, top-heavy. If you have a top-heavy rational function, which means the degree is bigger on the top, that means you don't have a horizontal asymptote at all. And you would just say none. You don't want to leave it blank, right? You don't want to leave blank space. You would just say none. There isn't one. Okay? This little note, so you guys can remember, sometimes you can cross a horizontal asymptote. I think I have 2 examples on here where we're going to see that on the graph. Crossing the horizontal asymptote is not really going to affect anything except for the range, because it's kind of going to cancel out what we were thinking about before in terms of range, because before the horizontal asymptote was interrupting our range and making it so that we had a number to jump over. If you're crossing over the horizontal asymptote, then you don't have that interruption anymore. So the only thing that this little idea is going to affect is the range, and so we'll talk about that when we get to those examples. And then again, in pre-calculus, something to pay attention to. Over here, we had 2 types of discontinuities that we're working with in this lesson. But in pre-calculus, there's actually another one called an oblique asymptote, which is another type of discontinuity. An oblique asymptote is diagonal. We have seen horizontal and vertical in Algebra 2. In pre-calculus, you gain a diagonal asymptote, otherwise called an oblique asymptote. And so where we said none before for the horizontal, you will learn if you move on to pre-calculus that instead of having a horizontal, you'll have oblique. That's not important for you guys right now. You don't need to remember that. That's just a little warning for those of you moving on to pre-calculus. If your numerator's degree is exactly 1 more than the denominator, then you're going to have an oblique asymptote. So that's just something to be aware of when you guys are moving on. All right, so that's the first thing you're going to find. Horizontal asymptote. Do not touch your function at all. Just look at the degree here and here, here and here. Look at your exponents of your leading term, and then use these rules to figure out what your horizontal asymptote is. Okay, that's phase 1. Once you finish phase 1, which is just the horizontal asymptote, now you're going to go ahead and factor both of the polynomials. You're going to factor the numerator if you can, factor the denominator if you can, and then cancel anything that they have in common. You want to simplify it. That's phase 2. So you have to factor and simplify, and then you're going to get a new function after you've crossed out stuff that you had in common if you're able to do that. So we have a lot of stuff that we're able to find after we simplify. So one of the things that they're going to ask you to find would be the discontinuities. Remember, we have two different discontinuities. We have the vertical asymptote and the whole. You could have one or the other or both. In our situations here, because we're talking about discontinuous graphs, there's no situation where you're going to have neither of them. You have to have either a vertical asymptote or a whole or both of them. Okay? So if you're doing a problem and you're like, I don't have a vertical asymptote or a whole, you did something wrong, because you have to have at least one of them. All right, so to find the vertical asymptote, it's going to work the same way that we did with reciprocal functions. The vertical asymptote is found in the denominator. I'm going to go back up really quick. When we were doing reciprocal functions, remember we said that the vertical asymptote was h, which was in the denominator. These are not in terms of h and k. You guys have to break that kind of thinking for these. We do not have h's or k's for these types of functions. That's only for reciprocal. For these ones, you have to think about it differently. To look for a vertical asymptote, you're just still going to be looking in the denominator. We're just not considering it to be k in this situation. So if there's still a denominator, you're going to set each factor that you have equal to 0 and solve for x. So like, for instance, over here, see how I have one binomial in here? I call that a linear factor. If I have one factor in the denominator, I would set that equal to 0 and solve. And that's how I find the vertical asymptote. The only time that you guys have a whole is if you were to cancel out something. So if you were factoring and you notice that something in the top and the bottom are the same and you cancel them out to simplify, that's when you have a whole. Remember, removable discontinuity, if you removed something by canceling. So the way that you find the whole is whatever factor was canceled, you're going to set that equal to 0. That factor that was canceled, set that equal to 0 and solve for x. Whatever you get for x, you're going to plug that into the simplified function to find the y, and then you would write it as a point. So your factor gives you the x value, and then once you find x, you would just plug it into your new equation that you got after canceling, and that's how you find the y. And again, I'm going to illustrate these all. I know it's just a lot of words and doesn't make a whole lot of sense, but I'll show you guys what I mean when we get to these examples. Again, we have not again, but we have a lot more to talk about for these examples. Finding an x-intercept. Since we already used the denominator to find the vertical asymptote, the x-intercepts are now going to use the numerator. Whatever factors you have in the numerator, you're going to set those equal to 0 and solve. You're going to write them as a point because an x-intercept is a point. So you're going to do exactly what you did for vertical asymptotes, but instead of using the denominator, you're going to use the numerator. If there is no x in the numerator, so let's say maybe the x canceled out somehow, then and you're only left with a 1 or just some other number. If there's no x, then there is no x-intercept. Right? You can't solve for an x-intercept if you don't have an x. So if there's no more x's in the numerator, it means that you don't have an x-intercept. To find a y-intercept, you're going to find it the same way that we always do. You're going to plug 0 into the expression for every x to solve for y, and then you write it as a y-intercept. Finding a y-intercept is the same no matter what your function looks like. So plug in 0 everywhere, and that's how you find it. Writing the domain and range can be a little bit more complicated. It's going to work in the general, the way that we write the domain is the same thinking that we followed for reciprocal. The only thing that's different is that now we could have a whole kind of affecting our graph. So the domain is going to be determined by the vertical asymptote, just like it was last lesson, as well as the x value of the whole if you have one. Okay, so not only will it jump over the vertical asymptote, it will also jump over the x value of the whole if you have one. So instead of just having, like last lesson, we only had it look like this, where it went negative infinity to a number, and then a number to positive infinity. You could have multiple jumps. See how I have a jump here and then another jump here? You can have multiple jumps here. A maximum of 3, I think, because you can have 2 vertical asymptotes, which is going to be weird. I know. I'll show you what I mean when we get to the graphing. But you could have 2 vertical asymptotes and 1 whole. I think that would be the maximum number of jumps that you guys would have. I'm not going to do that to you guys. We're not going to have one with 3 jumps. But you can have multiple jumps as you're going along. Similarly, the range is going to be affected by the horizontal asymptote and the y value of a hole if you have one. Right, so again, there could be multiple jumps in the domain and range because not only are you worrying about the asymptotes, you're also worrying about the hole if you have one. Okay, so a lot of information, right? So we're just going to go step by step in each of these questions, and we're just going to practice over and over again for different examples so we can see how to approach each of these different questions based on different examples. All right, so we're going to start with this one. Again, do not touch this. For phase 1, you don't want to do anything to your function. You want to put your pencil down and just look at it for a second. So looking at our function, we want to look for the degrees. I noticed that in this binomial, the exponent is a 1, and down here the exponent is also a 1. So the degree for each of our binomials here is a 1, okay? So the degrees are the same. So let's go over here and look at our rule. If the degrees are the same, that means the horizontal asymptote is supposed to be y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. So our horizontal asymptote is going to be y equals, okay, the leading coefficients are always the first numbers that you see that are in front of the x. Over here there's an invisible 1, okay, so the leading coefficient up here is a 1, and then the leading coefficient in the denominator is a 3. So according to our phase 1, because the degrees, the exponents were the same, I have to use this rule, and the leading coefficients are 1 and 3, 1 over 3. So this is your horizontal asymptote. That's all you have to do. All right, that's phase 1. Phase 2 begins by looking at this and seeing if there's anything you can factor and cancel. Both of these are binomials, and we can't factor binomials unless there's a GCF. There's no GCF in the numerator, and there's no GCF in the denominator. There's nothing I can cancel, right? Because you can't cancel x's because they're glued together with subtraction and addition. Remember, you can only cancel things if they're connected with multiplication. Be very careful you're remembering your rules for canceling. So there's nothing I can do to factor, oops, that's not what I meant to do. There's nothing I can do to factor or simplify, right? So because I can't factor or simplify, I just go straight into analyzing these new steps, all right? So again, finding the vertical asymptote comes from the denominator. So for discontinuities, I want to know, do I have a vertical asymptote? And if so, what would it be? Well, if you have a denominator, you have a vertical asymptote. All right, so our vertical asymptote is going to come from the denominator. And what you're going to do is you're going to set this equal to 0 and solve for x. All right, now because it's hard for me to write, just because I'm using my mouse, I'm not going to show the work. But you guys can do that over here in this space or wherever you guys want to do it. But if you set this equal to 0 and solve, you're going to get that x is equal to 1/3. It's not true that these will always be the same. It just worked out to be that way in this situation. All right, so don't think that the vertical and horizontal have to be the same. It just worked out that way for this example. So that's how you find the vertical asymptote. Look at the denominator, set equal to 0, and solve. There you go, vertical asymptote, done. All right, next thing that we're going to look at, discontinuities includes both vertical asymptote and hole. So I'm going to write 2 answers on the same line. All right, do I have a hole? Now, the way that you tell if you have a hole is, remember, if you were able to cancel something away, if you were able to factor and cancel, that means you have a hole. Now, because I wasn't able to factor or cancel anything, that means that I don't have a hole, so I don't have to worry about it, which is good, because once you throw holes into the mix, it gets more complicated. All right, so if you have a denominator, you have a vertical asymptote. If you didn't cancel anything, you don't have a hole, so that's what's going on in this situation. Okay, x-intercept. X-intercept comes from the numerator. If the denominator was already used, right, we used that up to find the vertical asymptote, all we have left is the numerator to help us find the x-intercept. So you're going to do the exact same thing that you did for the vertical asymptote. You're going to set this equal to 0 and solve, and that's how you find the x-intercept. So if I set this equal to 0 and solve, I'm going to get that the x-intercept is -7, 0. Remember, an x-intercept always has a 0 as the y value. You just have to find out what the x is, and then you automatically know that's a 0. So when you solve for x, you subtract the 7 over. That's why it's -7. All right, so set the numerator equal to 0 and solve, and write it as an x-intercept, and you've got it. Okay. For the y-intercept, what you have to do is you're going to plug in a 0 here and here. There's a difference between set equal to 0 and plug in 0. So for the vertical asymptote and x-intercept, I set them equal to 0. For the y-intercept, I'm going to plug in. It's a substitution. So I left a little space over here. I'm going to go ahead and show the work for the y-intercept. I'm going to replace x with 0 everywhere that I see an x. Not just one of them, but all of them. Once you've replaced all of the x's with a 0, all you have are a bunch of numbers. And once you figure out what this is simplified, that's your y value for your y-intercept. So if you go ahead and put this in your calculator, or you can do it mentally if that's something that you guys want to do, this would become 7 divided by -1, which becomes -7. So our y-intercept is 0, -7. And then remember, I put a 0 here because that's always what's true about a y-intercept. For a y-intercept, the x value is always 0. That's the definition of a y-intercept. So all you need to know is what the y value is, and you plug it right here. All right, I need you guys to be writing them as points, though. I mentioned that in the directions. Write as a point. Write as an x-intercept. Write as a y-intercept. I need points for each of these. I don't want just -7 written or -7 here. I need you to write it as a point. So make sure you guys are careful with where the 0 goes, whether it's an x-intercept or a y-intercept. All right, we're almost done. Now we just have to talk about the domain and range. So the domain and range, this is where you guys might want to bring out your colors if you guys are working with highlighters or colored pencils or something. It really helps me when I circle the things that are going to affect my domain in one color and then circle the things that are going to affect my range in the other color. Remember down here that the two things that could affect your domain are the vertical asymptote and the x value of a whole. So I'm going to come up here and I'm going to change colors to red. I'm going to circle everything that is going to interrupt my domain with red. The domain is interrupted by the vertical asymptote and then the x value of a whole. Well, I don't have a whole, so I don't have to worry about that. So the only thing that's going to interrupt my domain is 1/3. So when I'm writing the domain, it's all real numbers except for 1/3. And the way that we wrote that last class, it's going to be -infinity to 1/3. And then you jump over 1/3. And you can continue to positive infinity. Okay? So just like we did last time in our lesson, we still have the same setup. If you're jumping over a number, it just looks like this, and you just start at -infinity, end at positive infinity. All right? So your domain is going to look exactly the same as last time if you only have one interruption. If you have two interruptions, it's going to look a little bit different. We're going to see that in a bit. All right, I'm going to change colors to green. The things that are going to interrupt the range would be the horizontal asymptote and the y value of a whole. Well, again, we don't have the whole, so the only thing that's going to interrupt my range is the horizontal asymptote, which is 1/3 again. So my range is going to look very similar, because the horizontal asymptote and the vertical asymptote happen to be the same number, which is a coincidence. It will not always happen that way. Oops. Okay, and that is it. This is a full question that I would ask you for this lesson. All right. What's the horizontal asymptote? What are the discontinuities? What are the intercepts? What's the domain? What's the range? Okay, that is one question, all in full. Okay, and that's a simple example. They get a little bit more complicated as you go on, so just stick with me. We're going to start this one now. Let me go back to purple. All right, remember, phase 1, put your pencil down. Don't touch anything, don't write anything, just look at the function. The first thing we're going to look for is the horizontal asymptote by looking at the degrees. So if you look at the degrees for the numerator and the denominator, the degree for the numerator is a 2, and the degree for the denominator is 1. The bigger degree is in the numerator. This is top heavy. If the numerator's degree is bigger than the denominator, it's top heavy, you do not have a horizontal asymptote. So on the line where it asks for the horizontal asymptote, you're going to write none. There is no horizontal asymptote. All right, so there you go. That's it. All right, now we can go into phase 2. We can't find any of this stuff until after we start phase 2, which is factoring and simplifying. So we're going to look at what we have here, and we're going to see if there's anything that we can factor. So right away, I noticed that this is a trinomial. When you guys see a trinomial, that should remind you that we can use the X trick to factor. All right. I have not a whole lot of space, and my writing is really, really poor when I try to write here. So I'm just going to draw the x, and then I'll let you guys like do the factoring in your head or try to imagine how the factoring would work. You could use extra space somewhere. I don't know where, but for the x trick, I need two numbers that multiply to get 3 but add to get 4. The two numbers that do that are 3 and 1. Now, when you guys factor, when you do the x, or you finish the factoring process, all right, you can do that in here. My handwriting is too big. I wouldn't be able to fit it without making it too messy. When you finish the factoring process, you're going to get x plus 3 and x plus 1 as your two factors. All right, this is a binomial that can't be factored because there's no GCF. So this is what I get when I'm here, when I have the top factored and the bottom one can be factored anyway. So once you factor, now you want to see if there's anything that you could cancel that they have in common, top bottom. They both have an x plus 1 in common. So I'm actually going to cancel those out, which is just going to give me an x plus 3 left over right here. Right, so yeah, I didn't leave you guys a whole lot of room to factor. Hopefully you guys noticed, because we've been factoring for a really long time, there is actually a shortcut for factoring. When your leading coefficient is a 1, you should have noticed, as much as we've been factoring, that these two numbers that you guys get in the x trick are automatically the numbers that go here and here. So there's actually a shortcut to doing factoring a little bit quicker when your leading coefficient is a 1. If it's something other than a 1, like a negative or a 2 or something that's not a 1, you can't use that shortcut. You have to do the factoring the full process. But if it's just a 1 here, like there's nothing written in the front, you can just use those two numbers, plug them right in, and it's a little bit of a shortcut you guys can use. If that doesn't make sense, do the full process. If it makes sense to you that way, go ahead and do it. But there is a shortcut you guys can use as you get more comfortable with that pattern. But anyway, this polynomial shrinks all the way into this guy. All right, so we're going to be basing our phase 2 on this instead of this. All right, phase 1 for finding the horizontal asymptote has to be on this expression. Phase 2 is all based on this once you've simplified it down. All right, so discontinuities. Remember, discontinuities, there are two different types. There's your vertical asymptote, and then there's your hole. Okay, we need to see if there's one, both, or both of these. All right, one of either of them or both. So remember, the vertical asymptote exists when you have a denominator. Now this is an interesting example because we had a denominator initially, but then when we factored and canceled stuff, the denominator went away. So because our information for the second part of the question is all based on the simplified form, even though I had a denominator over here, if I don't have a denominator anymore after simplifying, then there is no vertical asymptote. That's why it's very important you guys remember what you're finding in each phase. All right, after you simplify and cancel, there is no denominator anymore. It's just x plus 3. There's no fraction anymore. So you can't have a vertical asymptote if you don't have a fraction with an x in the denominator. So that took a little bit of the work away now that we don't have a vertical asymptote to worry about. However, this is an example where we have a hole. So remember, you are going to have a hole if you were able to cancel something from your expression. And because we were able to cancel this factor right here, we are going to have a hole. And a hole is always a point. Okay? So the x value of your point, all right, to find the x value, you're going to take whatever you canceled and you're going to set that equal to 0. So the factor that we canceled out from the top and bottom was x plus 1. So if you set x plus 1 equal to 0 and solve, then your x value is equal to -1. All right, you have to subtract the 1 over, that's why it becomes negative. So for your hole, the x value is -1. The way that you're going to find the y value, and I wrote that right here, you're going to plug the x value into the simplified function to find the y value. So I'm referring to this guy right here, your new function, right? It's all based on this guy. We're not looking at this anymore. So you're going to take the -1 and plug it in for x. So -1 plus 3 is going to be a 2. There we go. So your hole is at -1, 2. All right, that's how you find a hole. If you canceled out something, whatever it was that you canceled, set equal to 0, get the x value, and then plug it in to find the y. Okay, so that's how you determine a whole if you're able to cancel something. Okay, so now an x-intercept. Remember, x-intercept comes from a numerator. So this one didn't have a denominator, but it does have a numerator, right? Technically, this is over 1, right? So even though when we write it like this, we have a denominator, that doesn't mean that there's a vertical asymptote, because remember, the x has to be in the denominator. So when you don't have a fraction, this is considered the numerator just by itself. So to find the x-intercept, remember, you have to set this equal to 0 and solve for x. If you set this equal to 0, you get that x is equal to -3. So our x-intercept is -3, 0. Okay? Now remember, for the y-intercept, the x value is 0, and in order to find the y, you're going to take the 0 and plug it in for x. So if you plug it into your function, you would get 0 plus 3, which is just 3. Okay? So the x-intercept came from setting this equal to 0 and solving, and the y-intercept came from plugging in 0 and figuring out what that number would be if you simplified. Okay, I'm going to switch my colors again. Remember, for domain and range, you want to switch your colors so you can identify what's going to affect your domain and what's going to affect your range. Okay, so remember, the domain is affected by the vertical asymptote and the x value of a whole. I don't have a vertical asymptote, but I do have a whole, so the x value, this guy right here, is going to affect my domain. So because I only have one thing that I'm jumping over, it's going to look just like what we did yesterday. Not yesterday, I keep saying that. Last class. It's going to be -infinity to -1, and then you're going to jump over -1 and continue to positive infinity. All right. However many things that you circle, that's how many jumps you have. So if I were to circle 2 things, I would have to jump and then jump again. But I only had one interruption, one discontinuity, so that's why I only have 1 jump. I'm going to change back to green. So for the range, the horizontal asymptote and the y value of a whole are going to define my range. Well, we didn't have a horizontal asymptote, but because we have a whole, I'm going to be using the y value to define my range. So that's only 1 jump, 1 discontinuity. So I'm going to have -infinity to 2, jump over 2, and then continue to positive infinity. Right? And that's my second example. So this one was a step up in difficulty when you have to factor and cancel, and then you have a whole. But everything else, you're still going to approach it with the same process and rule. All right, so just be careful as you're working through each example. All right, the third one on this page. All right, so again, phase 1, put your pencil down. Don't do anything. Don't draw anything. Don't try to factor anything yet. We're just going to look at our function, find the degrees, and then figure out which rule we're going to use for the horizontal asymptote. So I notice that in the numerator, I have a degree of 1, all right, and in the denominator, I have a degree of 2. So if we look back up at the rules, the denominator has the bigger exponent. So if the denominator is bigger, that means that your horizontal asymptote is automatically 0. That's just one of the 3 rules you guys need to remember. If it's bottom heavy, it's going to be y equals 0. Okay, so that's the end of phase 1. Once you finish the horizontal asymptote, now you guys can go ahead and start factoring and canceling if you can. So this is a simple binomial. There's no GCF, so I can't factor it. So I'm just going to write it as is. This is a trinomial, so I for sure can factor that. I'm going to draw the little x over here. The 2 numbers I need are going to multiply to get 2 and add to get 3. So you guys can do the full factoring process if you feel more comfortable with that. But again, that shortcut, the 2 numbers that multiply to get 2 and add to get 3 are 2 and 1. Again, if your coefficient is a 1, that means that you can go straight to put these 2 numbers into parentheses. I wonder how many of you guys picked up on that so far. All right, shortcuts are dangerous. That's why I didn't introduce it at the beginning, because shortcuts can be really dangerous because they only apply in certain situations. So I'm telling you guys now because I feel like you guys are comfortable enough with factoring that if you don't remember the shortcut, you can still factor using the old method. But just be very careful if you're going to try to use shortcuts that you understand when to use them and when not to. Okay? And just a reminder, you can only use a shortcut if there is no number in the front here. Okay, so now that I look at this, I notice I can cancel out the x plus 1 because they have that in common top bottom. This, you guys have to be really careful. If I cancel out the x plus 1, there's no longer anything in the numerator because it divided away, but you can't just leave it empty And you can't just pretend that the x plus 2 moves to the numerator. The x plus 2 is stuck in the denominator, right? If it was in the denominator to begin with, it has to stay there. It just lost its friend, right? They canceled each other out, so now it's alone. But if you don't have anything left over, like it cancels away, you guys have to write a 1. Right? You can't just leave empty space, and it's not a 0. It's a 1, because something divided by itself is a 1. So remember that rule. When you cancel something and you have emptiness, you have to put a 1 there as a placeholder. Okay, so now this is what I'm going to be looking at for phase 2. Ignore that, all right? This is what I'm going to be looking at to answer the following questions here. All right, so discontinuities. Remember, we have 2 types. We have our non-removable vertical asymptote, and then we have our removable hole. All right, let's see which of these or both that we have. So remember, a vertical asymptote exists if you have a denominator with an x in it. Well, we do, all right? We have the x plus 2 still left in the denominator, so that means we're going to have a vertical asymptote. And the way that we find that out is we're going to set it equal to 0 and solve for x. Because remember, the vertical asymptote is x equals something. So when you solve by subtracting, you get x is equal to -2. There's your vertical asymptote. Cool. All right, so the other kind of discontinuity is a hole. And the way that you know you have a hole is if you cancel something, if you removed something. So remember, it's a removable discontinuity. So I removed the x plus 1. So yes, I am going to have a hole. I just need to figure out where it is. So remember, to find the x value, you're going to take whatever it was that you canceled, set that equal to 0. If I do that, I get a -1. And the way that you find the y value is you take your x value, plug it in here, and then figure out what that number would be. So if I plugged in a -1 here, I would have 1 divided by -1 plus 2, which is a, excuse me, a 1. So it's 1 divided by 1, which is 1. And you can do that in your calculator if you want to, but you're just plugging in the -1 right here, and then you're good to go to find whatever the y value is. There you go, you finished your discontinuities. All right, x-intercept. Remember, x-intercept is found the same way that vertical asymptote is, except it's in the numerator instead of the denominator. But when you look at the simplified function, there are no more x's in the numerator. So remember, if there is no x in the numerator, you don't have an x-intercept at all. So because there are no x's to solve for, there is no x-intercept. So you just write none. All right, the y-intercept, all right, remember the y-intercept is 0, something. So I'm going to take 0 and plug it in for x everywhere that there is one. There's only one x right here. So if I plug in a 0, that would be 1 divided by 0 plus 2. And if you simplify that, it becomes 1/2. So the y-intercept is at 0, 1/2. All right, here comes the domain and range. Again, we want to pull out our colors. Red. Okay, so remember, the domain is interrupted or affected by the vertical asymptote and the x value of a hole. So I do have a vertical asymptote, so I'm going to go ahead and circle that because that's going to be important for my domain. I also have a hole. So this is a situation where both of these are going to affect my domain. So not only is it the vertical asymptote, it's also the x value of my hole. So both of these things are going to apply in this situation. So because I circled 2 things, that means I'm going to have 2 jumps. See how I had one jump here and then another jump here? I'm going to have to jump over -2 and -1. So the way that we write that is like this. Because we have 2 numbers and we're going from left to right, I have to make sure that I have the smaller number first. -2 is a smaller number than -1. So I'm going to jump over -2 first, like this. Okay, so if I go from -infinity and then I jump over -2, I'm going to keep going along until I get to -1, and then I'm going to jump over -1, and then continue to positive infinity. So if you guys have multiple jumps, you write the first jump here, and then you go immediately into the second jump, and then you just finish with your positive infinity. And this is how you would write your domain if you have 2 things interrupting your domain. Okay? Now, for the range is affected by the horizontal asymptote and the y value of the hole. I have a horizontal asymptote and a hole, so I'm going to use the y value. It's going to be the same kind of thing. -infinity, the first number that I would get to if I'm reading from the left is 0, so I'm going to jump over 0 first. And then I'm immediately going to jump over the other number, which is 1, and then finish at infinity. Okay, so this is what your example would look like if you have multiple things to jump over. You just go immediately into the next jump before you get to infinity. All right, so I have like one example of each type that you guys might see. One where you don't have a hole, but you just have a simple vertical asymptote, horizontal asymptote type thing. I have something where you don't have asymptotes, but you have a hole. And then I have the like all-inclusive, every single type of asymptote that you could have except for oblique and a hole. Basically everything all there. So I've hopefully given you guys enough coverage to see the different kinds of examples you guys will see, so that you guys can know how to practice with each different type. Okay, so we're going to go a little bit faster with these. These ones, they're exactly the same. We're just going to add on the graphing portion, which we're going to be doing primarily by hand. We don't really need our calculator to do very much of it unless it's one of the special cases. So even though we are going to be doing a lot of it by hand, you should probably still look at the picture in your calculator to make sure it matches. But we're going to start the way that we did before. Put your pencil down and look at what's going on here. You need to remember the rule for the horizontal asymptote. The degree is 2 for both the top and the bottom. If the degrees are the same, that means that you're going to write the fraction of the leading coefficient. So it's going to be -2/1 or just -2. So our horizontal asymptote is -2 because the degrees are the same. For discontinuities, I have either vertical asymptote or the hole. Remember, we can't find either of these two things until you've started phase 2, which you're going to do by factoring and trying to cancel. This is a monomial. Monomials are non-factorable. So if you don't see a plus or a minus or anything, you're just going to write down the monomial and then see what you can do down here. These are both perfect squares. You guys do need to be able to recognize perfect squares still, so you know how to factor those. Remember, the rule for factoring perfect squares is you take the square root of both of them and then you put a plus and a minus. Remember our difference of two squares? This is how you factor that. All right, so now that I've factored, there's nothing I can cancel. All right, they don't have anything common top bottom. There's no x minus 2 or x plus 2 in the top, so there's nothing that I can cancel. So this is just what I'm going to be looking at for phase 2. All right, remember vertical asymptotes come from the denominator. So I think I mentioned this very briefly before, but you can actually have 2 vertical asymptotes. Notice how this has 2 different factors in the denominator. So that means we're going to have 2 x's when we solve, because we have to set each of the factors equal to 0 to find the vertical asymptotes. So if you set each of them equal to 0, you're going to have 2 asymptotes, one at -2 and one at +2. So when we graph this, it's going to look way different than what we have seen before in the past with our reciprocal functions, but we'll get to that. But yes, it is a possibility to have 2 vertical asymptotes. You can only have 1 horizontal, but you can have 2 vertical. I don't think you can have more than 2. I am not 100% certain of that, but I've only ever seen situations where you have 2, at most 2 vertical asymptotes. Okay. Now, to know if you have a hole or not, you had to have canceled something, and because we didn't cancel anything out, we didn't remove anything, that means we do not have a removable discontinuity, so there is no hole. Okay? Don't have to worry about that. All right, x-intercepts come from the numerator, so you're going to take anything that's in the numerator with an x and set equal to 0. So I would take -2x², set that equal to 0. Because it's a monomial, if you were to divide by -2 and then take the square root, because it's a 0, that means it's automatically going to be 0 anyway. Anytime you guys set a monomial equal to 0, you're always going to get 0 back after you solve. It's just always going to happen that way, because when you divide or take a root of a 0, it's going to stay 0. So that's another shortcut you guys can use. If you set a monomial equal to 0, you're always going to get 0 back. Now, because the x-intercept is 0, 0, that means that the y-intercept was 0, 0. All right? Think about it logically. If you're crossing the x-axis right here, that's also where you would cross the y-axis, because that's where the 2 axes cross each other. So if you know that the x-intercept is 0, 0, you automatically know the y-intercept is 0, 0. Okay. Now, for domain, let's go ahead and use our color for domain. Remember, we're going to look at the vertical asymptotes and then the x value of the hole, but we don't have one. So I have 2 vertical asymptotes. So even though I don't have the x value at a hole, I still am going to be jumping twice, because I have 2 vertical asymptotes that are interrupting my domain. So I'm going to start at -infinity. The number I'm going to come to first is -2, because I'm coming from the left. So I'm going to jump over -2. And then I'm going to keep going until I jump over 2. And then I finish at infinity, like that. See what the picture looks like. You're going to start by drawing your asymptotes like we would have done last class. So my vertical asymptotes are at -2 and +2. So you're going to draw vertical lines at -2 and +2. You know, 2 vertical asymptotes. And then our horizontal asymptote is at -2, like this. Dun, 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 dun. All right, we have some other things that we can draw. We know that the x-intercept is 0, 0. So that's one of the points that we already know. All right, so we're going to draw that point. There's no hole, so we don't need to worry about that. So what you're going to do in order to figure out what the rest of the graph looks like is you're going to type this into your calculator very carefully. You're going to make sure that you have parentheses around the denominator. You don't need to have parentheses around the entire fraction this time, unless you would like to do that. So you're going to type in -2x² divided by parentheses x² minus 4 close parentheses. Just have parentheses around the denominator for now, and that will be good for this example. Now don't hit second graph. I don't want you guys to see the points. I want you to see the picture. So if you guys hit just regular graph so you guys can see the picture, you'll notice that it's going to look like this. Oops, I went a little bit too close there. Super weird looking, right? This is not what our... Put your pencil down, don't do anything, just look at the degrees. This is degree of 1, and this has a degree of 2. This is bottom heavy. Whenever it's bigger on the denominator, that's when you have y equals 0 as your horizontal asymptote. So horizontal asymptote is y equals 0. Done with that. Okay. Now we can start phase 2, our discontinuities. We're going to be looking for a vertical asymptote or a hole or both. I'm going to set up by writing these. But remember, you can't actually find them until after you have factored and simplified. All right, so x is by itself, can't really be factored. Down here, this is a binomial. I notice they both have an x in common, so I'm going to pull that out as a GCF. All right, and there's nothing more I can factor, but I can cancel those two x's out, right, which leaves me with only an x minus 4 in the denominator. And remember, if you cancel out the only thing that was in the numerator, put a 1 there as a placeholder. So now this is what I'm going to look at to find all the rest of the information. So a vertical asymptote comes from the denominator, so I'm going to set that equal to 0, and I get x equals 4 for the vertical asymptote. I'm going to have a hole because I removed something. It's a removable discontinuity. Because I removed the x, I'm going to set that equal to 0 because that's what I canceled. So that means that the x value is 0. To find the y value, I'm going to take 0 and plug it in. So I would get -1/4 if I plugged in a 0 and just did some mental math to figure that out. So my hole is at 0, -1/4. The x-intercept is supposed to come from the numerator, but because there are no x's, that means that I do not have any x-intercepts. The y-intercept, if I go ahead and plug in a 0, right, remember to find the x-intercept, it's supposed to be 0, something. So if I plugged in a 0, I'd get -1/4. Right. This is a very special situation. You guys can write this down for a second, but we're not going to be using it. If your y-intercept is where the hole is, the hole actually swallows up the y-intercept and then it doesn't exist. So if you guys have a hole and a y-intercept that are the same, the hole trumps the y-intercept and it kind of just swallows it up. So even if you get a value, it still doesn't exist. You would technically write none, because the hole was in the way. There really is no y-intercept because there was a hole instead. Right, so it's a little bit strange that you can find a number, but it doesn't actually exist because of the hole. Okay, now let's go ahead and look at the domain. Oops. All right, so for this one, when we're looking at the domain, again, you need to look at the vertical asymptote and then the x value of your hole. So this one's going to have 2 jumps. The number I would run into first would be 0. So I'm going to jump over 0 first because we're coming from the left. And then jump over 4. And then finish at positive infinity. All right. Excuse me. Hold on, let me check something because I think this might be the special case that I was going to introduce. Let me graph it really quick. Nope, this isn't that one. Okay, that's fine. All right, so for this one, let's go ahead and check to see what's going to interrupt our range. All right, so the horizontal asymptote and the y value of the hole are going to interrupt our range. So I'm going to have negative infinity. The number we run into first is going to be the negative one. So I would go to negative 1/4, jump, go to 0, and then jump, and then finish at infinity. Okay. Now the way that this graph would look, let's go ahead and look at the graph. Again, go ahead and graph your vertical asymptote, 1, 2, 3, 4, right here. Oops. Your horizontal asymptote was at 0. All right, whenever you guys have a hole, what you're going to do is you're going to draw a little open circle around where the hole would be. So 0, negative 1, it's going to be very hard, but just draw an empty circle kind of as close to 1/4 as you can. If it's a little bit too big, that's fine, as long as it's in the general area. And then you guys are going to type this into your calculator and sketch the rest of it. So you would put this into your calculator, x divided by, make sure you have parentheses around the denominator. And if you plug that into your calculator, it's going to look like this. When you get to the hole, make sure you pick up your pencil, go to the other side. You don't want to draw through the hole. That completely undoes what the hole there is there for. So it would look like this. It looks more like what we did last time, but there's a hole in the way. So that's what this graph would look like. Okay. Okay, let's do the last ones. I know this lesson just continues to go on because there's a lot going on here, but we'll get these last questions done so we can finish. All right, so phase 1, we're going to look at the degrees. It is bigger in the numerator than the denominator, so this is top heavy. When it's top heavy, that means that you have no horizontal asymptotes. We're going to say none. All right, we do not have a horizontal asymptote. For discontinuities, I'm just going to set this up really quick. Remember, we have the non-removable vertical asymptote and the removable hole. We won't know what or which of these we have until we have factored and canceled. All right, so the top is a trinomial, so I'm going to use the x trick. Multiply is to get 6, but adds to get 5. That would be 3 and 2. You can do the normal factoring over here. You have actually room on this side now. You can do the factoring full out if you want to in this space, or you can use the shortcut I was talking about because the coefficient is a 1. You can do x plus 3, x plus 2 right away. All right, and then x plus 2 can't be factored. It's just a binomial. But these can be canceled, leaving me with just x plus 3. Over 1 technically, but you don't have to write the over 1. Alright, so this is like what we saw on the previous page. Because there's no x in the denominator, this is not technically a fraction right now. There is no vertical asymptote. So you can only have a vertical asymptote when it has an x in the denominator. We do have a hole though, because remember you have a hole when you cancel something. So I canceled x plus 2, so that means the x value is minus 2, so you have to set equal to 0 and solve. And then to find this, I'm going to take negative 2 and plug it in, so negative 2 plus 3 is going to be 1. So my hole is at negative 2, 1. Okay. X-intercept is supposed to come from the numerator. This serves as our numerator right now. All right, so I'm going to set that equal to 0. I would get negative 3, and then the y value is a 0. For a y-intercept, the x value is 0, and I would plug that in, and I would get a 3 for the y. Okay, so x-intercept, you set equal to 0 and solve. Y-intercept, you plug 0 in and solve to get the number. All right, for the domain, I need to use the vertical asymptote, which I don't have one, or the x value of the hole, which I do have. And so I would do negative infinity, jump over negative 2, and continue to positive infinity. All right, and then for the range, let me change colors. I don't have a horizontal asymptote, but I do have the y value of the hole, so I'm going to be jumping over 1. Finish at infinity. There you go. And then when I graph, again, you want to use your calculator to make sure you can visually see it well. So let me type it into my calculator really quick. Okay, if you guys have polynomials in both top and bottom, you want parentheses around both of them. I was not using parentheses for either of these because they were monomials. But if you have a binomial or a trinomial, like a longer expression with pluses or minuses, you do need parentheses around the numerator and denominator. So do parentheses x squared plus 5x plus 6 close parentheses divided by parentheses x plus 2 close parentheses. All right, I'm going to graph the vertical, oh, sorry, there is no vertical asymptote and there is no horizontal asymptote, so there's nothing to graph in those kinds of pieces in the graph, but there is a hole. So I'm going to go to -2, 1, there's going to be a hole right here. So I draw a little open circle around the hole. You guys are going to notice in your calculator when you graph it that it's just a line. So this really super complicated looking thing just simplified to become a line, like y equals mx plus b, right? The slope is 1 and the y-intercept is 3. Hopefully you guys recognize that, because this is really just an equation of a line. So the y-intercept, like I saw, was 3 and the x-intercept was -3. So I'm just going to use that to graph a line like this with a slope of 1. There you go. Something super complicated can actually look like a line if it simplifies out like this. Okay? So again, to guide you in graphing, because the graphs can't show horizontal asymptotes or holes. Like when you guys look at your calculator, you can see your graph goes straight through where the hole should be. Your calculator is not able to graph holes or horizontal asymptotes. They can only graph vertical asymptotes. So you need to be able to use your points and the information that you have in this little section to get a better idea of the graph and not just count on your calculator 100%. All right, our last one here, ironically, is the most complicated one, but once we get past that, we will be finished with these examples. So phase 1, I just need to look at the degrees, and they are both the same. All right, the highest power for both is a 2. So if they're the same, you're going to use the coefficients. This one's a 3, that one's a 1, so 3 divided by 1 is a 3. So our horizontal asymptote is y equals 3. Now I'm going to factor. Right, I'm going to factor the bottom one because that one's easier. You should notice that these two are both perfect squares, so you can just do x plus 3, x minus 3. The more you guys practice, the easier it is to see those rules for factoring, and then it becomes much faster, so you don't have to think about it too much. If you notice that you have a binomial where both of them are perfect squares, go straight into your rule for factoring perfect squares. Now this one's a trinomial, so this one I'm going to have to use the x trick over here. There are actually 2 ways to approach this. The first one, just use your general x trick where you do 3 times -24, which is, can't do that in my head, -72, and then try to find numbers that add to get -6. Or you could notice that it has a GCF of 3, and you can actually pull that out to begin with to make your numbers smaller. So if you divide everything by a 3, your numbers become a lot smaller and easier to work with, right? So you could do the multiply and do the x trick and all of that. You'll get to the same answer either way. But if you pull out the GCF first, it can actually make the x trick easier for you because the numbers get smaller. So when we pull out the 3, we divide everything by 3. The x trick would then be what multiplies to get -8, but adds to get -2. Well, the two numbers that do that would be -4 and +2. Now once I pulled out the 3, now that the 3 is outside of the parentheses, now there's actually a 1 in front of the x squared, so we still get to use the shortcut I was talking about before. I get to go straight to x minus 4 and x plus 2, like this, because I was able to remove the 3 as a GCF. If the number in front of the x squared is not removable as a GCF, then you cannot use the shortcut. So like if this was a 5, because it's not a GCF, I wouldn't be able to do the x trick and then just take those two numbers. I can't do that. It's only when you're able to have a 1 as a coefficient, a leading coefficient, after pulling out a GCF, if that's something that you would have to do. All right, again, if you don't like that shortcut, just use your x trick process, do it all along the side, and you'll get the same answer either way. All right, unfortunately, nothing cancels, so even though this looks pretty messy, this is how we're going to want to keep it so it's easier to work with so we can find the following information. So discontinuities, I'm either going to have vertical asymptote, a hole, or both. So for vertical asymptotes, remember we're going to find those in the denominator. I have 2 x's, which means I'm going to have 2 vertical asymptotes. If I set each of those equal to 0, I would get -3 for this one and +3 for this one. So I'm going to have -3 and 3. 2 vertical asymptotes. You're going to have 1 asymptote per factor, or per x. There's no hole, because I didn't cancel anything. So moving on from that. x-intercepts come from the numerator. I have two x's, that means I'm going to have two x-intercepts. Remember, you're going to solve for them the same way we did down here. We're going to set them both equal to 0. So if I did that, if I set x minus 4 equals to 0 and x plus 2 equal to 0, I would get positive 4 and negative 2. And remember, always write them as points, as x-intercepts. So I would get positive 4 and negative 2 as my x-intercepts. Again, 2 x's means 2 x-intercepts. 2 x's in the denominator means 2 vertical asymptotes. Okay, y-intercept, you can only ever have one of these. So you're going to plug 0 into every single one of these x's. There are 4 x's. You're going to plug 0 into all of them. This is probably where you would want to use your calculator. It would be easiest to just use your calculator. So if you plug in the zeros and just plug it in as you see it, type it all in, use your parentheses really carefully, you should come out with, well, I wrote it down. As a decimal, you get 2.6 repeating. All right, so when you plug in a 0 here, 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 and here, and then type in the numerator, figure out what that is, and then find the denominator, and then divide them, you should get 2.6 repeating. All right, this one has a special range. So I'm actually, you wouldn't need the picture, but for this one, you do need the picture. I want to show you the special case that I mentioned before with passing through the horizontal asymptote. I want to show you guys what it would look like if you are actually allowed to do that. So we're going to type this into our calculator, put parentheses around this and this, and you put it into your calculator. So parentheses 3x squared minus 6x minus 24 close parentheses divided by x squared minus 9. By the way, you want to type this into the calculator, not this, because there are way too many parentheses and you're going to get messed up. So whenever you're typing it into the calculator, always use the printed version of the equation. Now hit graph. All right, so let's take a look at this. So I do have my vertical asymptotes at -3. Didn't really need the calculator to find that because I had that written down already. 1, 2, 3. I have a horizontal asymptote, which as you guys can see in the graph, it's not drawn, but you do actually need to draw it. We have a horizontal asymptote at 3. My x-intercepts are at 4, 0, and -2, 0. And my y-intercept is like here-ish. I know it's a decimal, so you have to estimate. Now, all you have to do is look at your calculator to see what's happening. I have this little piece here. I have this in the middle, and then I have this over to the side. So this, look at that. It's crossing the horizontal asymptote. So this, because we didn't have a hole and the horizontal asymptote didn't interrupt us, the special range here is actually going to be all real numbers. There's no interruption. We didn't care about the horizontal asymptote. We went right through it. So we're going up and down forever without being interrupted. So this would be a special case where the range would be all real numbers. No interruption, no jumps. So again, you wouldn't know that unless you saw the graph. So just be aware that I'm not going to give you any question like this on a series assessment, but they do exist. Now, the domain, however, there are not going to be any special cases for the domain. It works the same way every time. So again, I need to use these guys and the whole if I had one, but I don't. So for the domain, it is going to be interrupted by both -3 and +3. Right, so really the only special case situations are your range when you have crossing through the horizontal asymptote, and then this thing where your hole and your y-intercept happen to be the same, in which case your y-intercept would go away. Those are really the only special cases you guys are going to potentially run into but not be assessed on, right? So that was a really long lesson. This stuff takes a lot of practice, so make sure you guys are taking the opportunities provided. If you need more practice beyond what's in the homework, I can find more examples.